guys and girls. Three-phase circuits. So, tonight's session, we're going to look at why do we use a three-phase system? Why do we have, I'm going to give you reason for there being a three-phase system. A number of reasons. We're going to look at the relationship between the line and the phase voltages and line and phase currents for both balanced star and delta connected systems. We'll look at power in balanced star and delta connected systems. We're going to look at solving some problems around those three-phase systems. So, if we had, first we'll look, if we had well, we do have in some cases, single-phase systems and generators, small systems that you see on building sites and things. So, if we look at that, we've got imagine a permanent magnet generator. We've got a field here, and if we turn that in proximity to those conductors there, we would generate an EMF in position because we'd be, if you imagine this going round, the field would be cutting across that conductor, and therefore by laws of magnetism would generate an EMF and a current would flow in the winding. When the permanent magnet is in this position, there would be no EMF generated. So, the generated EMF is given by E is equal to B times L times V. B is the magnetic flux density, L is the length of the conductor in the field, and V is the velocity relative, the velocity across the conductor. Yeah. So when the coil's not in the field, there's no voltage induced. So if we look at that simplified generator as us going around, we get a waveform that looks like that, which is a cosine waveform. And that's just based on where I started from, position where the maximum voltage, minimum voltage. So we turn 90 degrees, we go from there to 0. We'd then be the opposite way round with the poles, so we get a negative peak, and then back to 0, back up to a positive peak again. Okay, everyone all right with that? And we've probably done that before on a lower level course anyway. So that would be the voltage output waveform. If we consider the power in a single phase system, so if we connect a load to that simple generator so that a current flows, I, through a load represented by a resistance, we get some power in watts. Okay, so the sinusoidal voltage produces a sinusoidal current flow, and at the moment we're keeping things in phase by just using resistance. Okay, so there's no phase shift here, just blue is the voltage produced and the red is the current. If I then calculate instantaneous power by multiplying instantaneous current by instantaneous voltage, we would get a power curve that is pulsating, like this blue curve at the bottom here. All right. Notice that it goes down to 0, peaks at 200, never crosses the 0 line. Okay, it's resistive, so therefore we've got no Q, everything is above the line. And the frequency of it is doing 1, 2 cycles for every cycle of the generator. What that's doing is that's presenting a pulsating load to the primary mover that's rotating it. So if you're driving this generator with a turbine, water turbine, steam turbine, the load you're putting on that turbine is pulsating. It's not constant. So that's a disadvantage of single phase generator. It has a tendency to make them noisy because of that pulsating load. And all your bearings are getting a pulsating load on them and so on. Okay? Yeah. Any questions so far? So, if we go two-phase, so let's say we added a second coil, 90 degrees around the stator to the original winding A, got the same permanent magnet, so we produce an identical sinusoid that's 90 degrees out of phase with the first one. Yeah. So what we've got now, one phase is a sine wave, the other phase is a cosine wave, which is 90 degrees out of phase. So the blue one is volts to the A coil, and the red one is volts for the B coil. All happy with that? Yeah? If we then consider the power produced from there, so we connect a load to both of the windings, when the power from each of the coils is added together, the overall power is a constant. So that's the power for A, that's the power from B. We do an addition of those two powers, we get a straight line at that peak of 200. Okay? There's no real numbers been applied here at this stage. That's just the peak I chose in Excel when I wanted to draw these graphs. All right? So therefore, we're presenting a constant load to the prime mover. And adding a second winding has got us from having a lumpy output like, where's that first one? Not on that page, is it? What's that? There, down the bottom. That's it. From a lumpy power output, where the average is going to be about 100, roughly, watts. Yeah, it's not quite. I'll be in here somewhere between 100 and 150. Yeah. To having the full 200 in this example. Yeah. So that's two phases. So the extra power is produced without any increase in the size of the generator. Just put a second coil 90 degrees out. Two-phase system. All things being equal, every phase being exactly the same and balanced, that'll be a straight line. But we're talking in theory now, yeah? Of course, in real life, nothing is as it would be in theory, is it? Yeah? So, yes, some, but you're going to be presenting a much smoother load to the prime mover. Alright? Yeah? The first one you're going to do nothing about, Lewis. There's nothing you can do about that, because that's only a single phase generator, so it can only have a single phase load, so you can't do nothing about balancing out that problem. Alright? So if we then go one step further and add a third winding, so if we look at winding A and winding B, they're 120 degrees out of phase with each other, and winding B and winding C, A and C that way, are 120 degrees out of phase with each other. So we've got three phases with 120 degrees between each of them, wrapped around the stator. Okay, so we add a third coil, yeah, to the generator, angle of 120 degrees between each coil. We get 3 sinusoidal waveforms, 120 degrees at a phase of each other. If we look at the powers, they're all above the line, yeah, and they're all 200 high. When we add them together, we get a straight line, all being equal at 300. So when the powers produced from the 3 phases are summed, it produces a constant power output that is 1.5 times what you get from 2 phases. Yeah. This is 3 times what we got from the single phase generator with little or no increase in generator size. Now you might say, why don't we go 4 phase, 5 phase, 6 phase? But you'll then be getting into the stage where you will significantly increase the complexity of the machine, its overall size for a given output, and laws of diminishing returns in terms of how much extra power you get out of it. We get the other thing that we get from this is that nice rotating magnetic field that we want for our induction motors that we talked about a couple of weeks ago. Yeah. Okay. So that kind of gives you a little bit of background as to why you have a 3-phase system. What we've got to then do is cover why we have 2 differently connected 3-phase systems. Yeah. So, balanced 3-phase circuits. 3-phase power system will have a star, or the Americans often say a Y connected. So generally in this country we talk about star, but if you look in textbooks, some of them will talk about Y. Yeah. Each phase displaced by 120 degrees. So we've got EA, EB, and EC, all with 120 degrees between them. When we get on calculations later, we'll start to give one of these a positive 120 degrees and the other one a negative, from this one being 0. That's how we'll deal with that calculation wise. Alright? So you'll have a star generator with each phase displaced by 120 degrees. It's called a balanced source. The generator can have loads connected in either star or delta. Okay, you don't see, or I don't know of, delta connected generators. The reason being is, if you had a perfectly balanced load, all would be okay. But if it isn't balanced, what you'll start to get is generator, and you've got over here connected to that an unbalanced phase load. Well, it's difficult to achieve. You'll end up with currents that just flow round the delta and just heat the windings up. That's not what you want. So generator connected to star, and all the generator diagrams I put on the board will have the generator connected in star. Well, where you have access to them, they're connected in star. You know where you transform down from 11 kV to 415, you're going down from 11 kV delta to 4. Yeah. So the main transmission system is 3-wire delta connected stuff. All right. One less cable. You go to star, so you can make the 4th wire and get the neutral point in the middle. We're coming on to that in a minute. All right. Yeah. So if you've never seen beyond the 11 kV system in detail, then you won't see transformers connected in delta usually. All right. So, I've got a note there about generators rarely, if ever, connected in delta, because if the load's not balanced. Furthermore, the phase voltages are lower in star connected system, meaning less insulation is required. Yeah. So a lot of your high voltage delta system transmitting around the country is bare conductors anyway. Yeah. So if you keep if the voltage is lower between lines, which you get a lower voltage between lines in star, then you don't need so much insulation to keep them separate. All right. So star connected load we'd draw like so. The one on the left, delta connected load, drawn like a triangle. All right, and you can see if you turn that one up the other way, that's the American Y connected. They do call that one delta. All right, yeah. Anyone not come across star and delta before? At all, ever? No? You have or not? Not. You've never heard of it before? No, not in work, but in learning you have. Oh, okay, yeah, because they're three-phase generators that you're building that, aren't they? Yeah. Okay, relationship between phase and line voltage for a star-connected system. There's a relationship between phase voltage EP and line voltage EL that can be determined as follows. Right. Pause that. Right. If you look at the voltages here, this line voltage between, if I call them red phase and yellow phase, I make no apologies for using the old colours. All right. Whereas these voltages are phase voltages between lines and neutral. So if you look at any one of those line voltages, the one between red and yellow is made up of EA plus EB. Yeah? But what you have to remember is they're not in phase with each other. Yeah? So if we say these line voltages, sorry, these phase voltages are 100 volts. Yeah. Then in this angle in here is 120 degrees. EL is equal to 100 angle 0 degrees plus 100 angle 120 degrees. Yeah. Yeah. I know why I was doing that, because no, I don't. If you do it this way, your complex numbers will handle that situation. Right, so let's just convert those. So that's EL is equal to 100 plus 0J plus 100, and then you've got to do to convert that 100 angle 120 to complex. Pardon. Right, there's an easier way to go through that than this. So if we draw a phasor diagram of this relationship, we get the following analysis. Let's just go back to your question about this, Robbie. EL and EA being one minus the other. If we give a direction to these, that one arrow is in one direction, EB is in the opposite direction. So that must be negative. So if we say EA is positive, then EB must be negative because the arrow's the other way round. Alright, so that's where that comes from. Remember Kirchhoff's voltage law, you have to have direction to your arrows. Alright, so that's where that comes from. So, drawing a phasor diagram. Here's EA, straight upwards. This one here. I'll draw over it in red, being the red phase. That's the phase current for phase A. I ain't got a yellow. Never mind, I'll use green. EB would be this way, minus EB is a complete opposite angle. Yeah? And then our resultant comes in that parallelogram. Alright? So we've got a triangle now where we can apply the sine rule to this triangle here. If that angle's 120 in there, and because this is a parallelogram, this angle and this angle must be equal. So the all three angles add up to 180. These two must both be 30. So we apply the sine rule. One side of the opposite angle is equal to the other side of the opposite angle. Do you remember the sine rule? Sine A of a sine A equals B of a sine B equals C of a sine B. Rearrange that for the line current. So the line current is E phase sine 30. Okay. If you then put this bit in your calculator, sine 120 degrees over sine 30, you'll find that the result is try that, root 3. Hopefully you're, in summary from that, it's always true. For a star connected system, the line voltage is equal to root 3 times the phase voltage. Equally, we can say E phase is EL over root 3. So if we know one, we can always find the other one. Yeah? And that is in star. So for a star connected load, line voltage is root 3 times the phase voltage. So the issue is you've got two phases of, in our example, 100 volts added together, but you don't get 200 volts because they're not in phase with each other. Yeah. So for a phase voltage of 100 volts, what do we get? What is 100? 100 times root 3. $173 volts. So a line voltage of 173 will give us a phase voltage of 100. So if our line voltage is 400, EL equals 400. What is E phase? 400 over root 3 230. Yeah. So that's where your 400 and your 230 come from. All right. So on your systems that you're used to, you've got a dual voltage system because you get 400 volts between phases and 230 volts between phase and neutral. Yeah. So in a star connected system, your voltage, the line voltage is two of the phases added together, but we have to take into account the fact that they aren't in phase. So what you get from the whole system is three line voltages that they'll be 120 degrees out of phase with each other and 30 degrees out of phase with their respective, with each of the phase voltages. All right. Phase and line current for a star connected system. So over here is on the left is our star connected generator. Okay. We have a current flowing down the top line. It goes through a load, and then most of the systems you'll come across, the star point of the generator is connected to the star point of the load, creating a neutral. Yeah. So we get a current flowing in there, and it's one current back down the neutral to the other side. Second phase. So the line current, this is the line from generator to load, is exactly the same as the phase current, because all the line current goes through one load phase. All this line current goes through that load, all that line current goes through that load. And all the three currents added together flow through the neutral. Yeah. So in star connected systems, I line is equal to I phase. And these things you've got to try and remember, be able to sketch a diagram and see that all that current going down that line has to go through one load. Yeah? But when you look at it voltage-wise, this voltage and that voltage add together to become the line voltage between those two. So in star connected, line voltage and phase voltage are different, currents are the same. Yeah? Right? So, if the star connected load shown above is balanced, and the three phase currents IA, IB and IC are equal in magnitude and also equal to the line current. Right? So, if we say got currents of 1 amp in each line, i.e. balanced, current in neutral equals what? I mean, what does Kirchhoff's current law say about a node? We've got a current down there, current coming that way, current going that way. If all of them are going in, yeah, leaving must be all of those IA, IB and IC added together. So you say that's 3 amps. What's wrong with it? No, it'll turn, all the load will turn electrical energy into some other form, heat, etc. Exactly. So, Kirchhoff's law says, Kirchhoff's current law, IN is equal to those 3 added together. Yeah. But they are IA, if IA equals 1 amp angle 0 degrees, IB 1 amp angle 120 degrees, IC 1 amp angle minus 120 degrees. Convert all of them to rectangular or flow in the neutral. When you take the angles into consideration, you should find when you add them all together, the balance system, you'll get no current. Alright? And when we start looking at some unbalanced systems later, faulted systems, you'll find that you then do get, if you take one of the phases away, you get a current flowing in the neutral. We put unequal loads on. Right? Boys, yeah? So the natural thing is to think you add them all together. That's 3 amps. But the angles mean they cancel out. Right? So that is star connected. I've got one slide at the end, I think, that summarises both systems on the same. So, relationship between phase and line current for a delta connected system. Okay, in this diagram up the top here, we've got a current flowing IA in the line. And at this node here, we've got one current flowing out and another one flowing in. So it suggests that line and phase currents are different in a delta system. All right? IA is I1 minus I3. If you apply the arrows going in, arrows going out law, you'd say IA plus I3 is equal to I1 here, and then rearranging that for IA, that must be I1 minus I3. Yeah? So, again, if we draw a phasor diagram where I used IA there, didn't I? It's the line current, yeah, and then we're drawing the phase current, and I3, I1 that way, minus I3 up that way. We've got this triangle again. We use the sine rule, IL over sine 120 is equal to I1 over sine 30. Again, that comes out as root 3. Okay, so in a delta connected system, the line current is root 3 times the phase current. Yeah. Equally, I phase is equal to I line over root 3. I'll write that a bit bigger over here. I line is equal to root 3 times I phase. Yeah, I know. I have gone a bit funny here because yes, I won, but it's any one of the. You have to be a bit careful here because there's 3 different line currents and there's 3 different phase currents. Each one of the line currents is equal to √3 times the phase current. Yeah. Yeah. I phase is what's going through a single load or phase of the load, and I line is what's coming down the lines that supply that load. Yeah? Alright? Because if this is a delta connected motor, Lewis, if it's a delta connected 3-phase motor, right, you're going to get a phase current of, let's say, 10 amps in each winding. There's going to be √3 times 10 amps flowing in the cables that go to it. Yeah? Okay? Does that help to... Yeah? If you supply in star a 3-phase motor, which wouldn't have a neutral, then you'd have 400 volts between the cables that supply it, but each winding is getting 230. Yeah? So if you have a star motor versus a delta motor, in star the motor's getting 230 volts a winding, in delta us getting 400 volts a winding. Right? So, star delta summary. Just to summarise, got one slide summarising to be useful. In a star connected system, a line voltage is √3 times the phase voltage. Line current and phase currents are equal. You get 3 line voltages 120 degrees out of phase with each other, and 3 phase voltages 120 degrees out of phase with each other, and 30 degrees out of phase with the respective line voltages. As opposed to delta connected system, line current equals √3 times the phase current, line voltages equal to phase voltage. If we go back to that delta system, didn't specifically talk about it, but here's our line voltage, and each winding is getting line voltage. Because this winding here is getting the line voltage between A and B. This one is getting the line voltage between B and C, and this one is getting the line voltage between A and C. Yeah. So line voltage and phase voltage in delta are equal. You get 3 phase currents 100 degrees out of phase with each other, 3 line currents 120 degrees out of phase with each other, 30 degrees out of phase with the respective phase voltages. Yeah? Questions? No? Yes, there is. There's a mistake there. That should be currents coming in there. All right. The main thing about delta connected systems is they really need the load to be as balanced as possible, because otherwise you're going to get this delta currents going around the delta. So a motor is generally pretty close to being balanced, whereas when you get things, if you was to connect different people's houses onto a delta connected system, you're going to get an imbalance in load when people are turning things off and on. All right? So the neutral helps to handle that. Okay, power. 3-phase balanced load. So, for the circuit shown, the apparent power to each impedance is. So, we got a star connected load. Each of these phase voltages is EL of a √3 from what we've just been doing. Yeah. So if we take S for each load is EL over root 3, that gives us phase voltage, multiply it by the current, so the total apparent power is actually 3 times them. So what it's saying here is you can calculate the power for one phase and then multiply it by 3. Yeah. So the total power is 3 times EL times IL, root 3 times EL times IL. Yeah. Furthermore, since phase voltage is given by EL over root 3 is equal to EP, we can say the total apparent power is 3 times E phase times the line current. Right? Or not? If you don't understand where this come from, do 3 over root 3 in your calculator. To root 3? Yeah? Right? So all I've done here is instead of putting EL over root 3 in, I've put EP in. So what I'm saying is you can get the apparent power from either phase voltage or line voltage divided by root 3. And you get this EP times IL will give you the apparent power for one phase, multiplying it by 3 will give you the total power. Yeah? Have you got everyone okay with that? Any questions? So, power for 3-phase balanced load connected in delta. For the circuit shown, the apparent power to each impedance is so in these delta connected system, the phase current is IL, the line current, divided by root 3. So if we take that, so IL over root 3 is the phase current, multiply that by EL, we got the apparent power for one load. Therefore, if we want the total apparent power, we multiply that by 3, we get a total apparent power as root 3 ELIL. Please note, although that formula is the same as on the other page, root 3 ELIL, it does not mean that the power, the apparent power in a given load, so the same load connected in star and delta, will not give you the same power. That's not what it means. Because remember, the different systems have got different currents and voltages. Okay? So I didn't want that confusion to happen. The formula is exactly the same, but you won't get the same result connected in the two systems. Furthermore, since phase current is given by IL over root 3, we can replace IP in that formula, so the total power can be calculated from 3 times EL times IP. Alright? So that's all the stuff about the two different types of systems and how we do calculate, or where the calculations come from, and why, in a way, why we got the two systems. So we have delta for the main transmission, and we use that with delta connected motors as well, but usually delta loads are where you got a nicely balanced load. Whereas star system allows for imbalance by having the neutral conductor. Yeah, so again, you're all right connecting your motor without a star neutral connection because that's generally balanced, but other multiple loads won't be. All right. Well, yeah. If when we have a look at some imbalanced loads, what do you mean when one winding go open circuit or partially short circuit? Yeah, well, but that's going to change the current that's flowing in the other two as well. Please wait till we get to that bit. Yeah. All right. Yeah. So let's have a look at a problem then. A three-phase motor is connected to a 440 volt line and draws a current of 5 amps. If the power factor of the motor is 0.8, calculate. Okay. Three-phase. I should have put in star 240 to 440 volt line. So, always worthwhile sketching the system. So there's my three-phase motor. It's connected to 400 volt line. Alright, and it draws a current 5 amps. .440 volt, yeah, sorry. .440 volts, 5 amps. Right, calculate the total apparent power, the total active power, and the reactive power absorbed by the machine. So this also dips back into what we've done before with active and reactive power, as well as the new stuff that we've done. So A, how do we go about calculating the total apparent power, ST? Given the information that we've got, we've got line voltage, EL, and we've got line current. Answer is 3.8 kVA. Be near enough for us. Yep. So, B, how from that can I find active power P? What will help me? What other piece of information have I been given that will help me do that? I can start to draw this power triangle, can't I? I've got S is equal to 3.8 kVA, and I've got cosine of that angle is equal to 0.8, I think it was in the question. Yeah. So cosine 0.8 is equal to P is the adjacent side, yeah. Therefore, P is equal to 3.8 times 0.8. Yeah, I mean, if you, yeah, yeah. Well, if you leave it as kVA here, then your answer is going to be in kilowatts. Yeah, all right. And if you've only got two significant figures there, then you should really only have two significant figures here. So that should be 3.0 kilowatts, really. All right. We'll leave it as it is, but that would be what you would do. And what's 48 watts in 3,000? That's not that significant. All right. And then C, it says reactive power. So we want to find Q. How would you do it? It's equal to root S squared minus P squared. That's root 3.8 squared plus, sorry, minus 3 squared equals. Yeah, 2.3 kVAR, so the same number of significant figures as the others. Yeah. So that's dipped into calculation work that we've done in previous weeks. That shows you how you can find the power in a three-phase system. All right. So solving three-phase balanced load problems. Balanced three-phase load may be considered to be composed as three identical single-phase loads. Consequently, the easiest way to solve each circuit is to consider only one phase. Following examples illustrate the method to be employed. Okay, so what I'm saying there is, if that's balanced, you calculate for one, and because it's balanced, they're all going to be the same. Size of current-wise. Remember, you're always going to have phase differences. All right. So, three identical resistors are connected in star across a three-phase 550 volt line, dissipating a total active power of 3,000 watts. So let's just have a sketch. line voltage EL equals 550 volts. PT, total power, 5 kilowatts. Sorry, 3 kilowatts. Put 3 back. Right. And the question says, calculate the current in each line, the value of each resistance, and the total power dissipated if the same load is connected in delta. Right. So, first, what's an important thing about the fact that it's a resistive load? Or a purely resistive load, I should say. Yeah. One other important thing. And ST is equal to PT. We've got no power factor there. Yeah. So what do we know in terms of formulas for T? Because we've been, in this case, 3,000, because we've been asked to calculate the current in each line. Yeah, we've been given the line voltage, not the phase voltage. So how can we handle that? What's a formula involving line voltage for ST? So, line current, 3.15 amps. So how can we find B, the value of each resistance? We now know the current flowing through each one. 3.15 was it? Amps. We've got the line voltage. If we can calculate the phase voltage, we can use Ohm's law, can't we? So how do we get phase voltage from line voltage? EL over root 3 divided by the current. Yeah. Whichever one of those two voltages you've got, you can always get the other one. Yeah. So in this case, we know the line voltage, but we need the phase voltage We just divide the line voltage by root 3. So that's 500 over root 3 divided by 3.15. Where did what? Out of my head. 550. I got 100 ohm. Where's Ben gone? I got 100 ohms anyway. Hopefully you get the same. Right, 100 ohms, yeah? So the last part of the question, remember that the 100 ohm per phase load draws a current of 3.15 amps, okay? Total power, 3 kilowatts. If we connect that same load, I'm going to use a new page, to delta, to the same voltage. So we've got 100 ohms, 100 ohms, and 100 ohms, all connected to a 500 volt line in delta, 550, sorry. What is the total power? Right? So, how can we go about this? Anyone see they would tackle that problem? Remembering what we said up front about balanced systems. Balanced system so calculate for one phase and then multiply by 3. Yep. So I phase, this is a phase current, single 100 ohm resistor, that's got 550 volts across it. So in this case that's EL over R, 550 over 100, 5.5 amps. Yep. As opposed to 3.15 in star. Yeah. So power for one phase equals You do it like that. That is not 5.5 amps here. It's 5.5 amps here. We can do IP squared times R. Don't we? 5.5 squared times 100. What's it? So 302 pi per phase. Yeah. Therefore, £9,075 watts. Star, yeah. Star limits the starting current. Yeah. There's torque, start and torque differences as well. So you get torque to go and then change over at delta. I'm not an absolute expert on everything motors, if I'm honest. Know enough to get by, but there's such a minefield of differences. Nobody, unless you're working for someone like Lawrence and Scott Electromotors, you're not going to know all the details. Yeah. Right. Let's have a look. See what else we got here. Here now we're going to have some fun. First of all, how is that load connected? We got 3 4-ohm inductors or windings with their series resistances of 3 ohms each. How are they connected? Star or delta? Star. You're looking for the classic one end of all of them connected together, must be in star. So although they aren't drawn in that star shape, you can recognise that that's how they're connected. Yeah? For the circuit above, calculate the current in each line and the voltage across the inductor terminals. So star connected, we've got EL is equal to 440 volts. Yep. And what we got impedance wise? What's the phase impedance? One phase, ZP. How could I express that? How am I going to get this current? What if I said to you, I want the magnitude only? How would you do it? So I'm not interested in angles. Just want to know how many amps are flowing in each phase. What's the quickest way of getting the polar magnitude out of that? Remember what that is? It's 3 this way, 4 that way. Yeah, so use, if that was more complicated numbers, you'd say five ohms. Yeah. And you remember here we've got it. We've been given EL, right? The line voltage, 440 volts. So I phase is equal to E phase over Z phase by Ohm's law. Yeah. How can I rewrite E phase with the information I got? And given EL over root 3 divided by Z phase. So that's 440 over root 3 divided by 5. 50.8 amps. And again, all we want is the magnitude of VL. How can I get that? Ohm's law, IL times XL, which you've been given. 50.8 times 4. I've got 203 volts. Right. Now that we'll be moving on sometimes later on a module where we will be interested in the angles. But at this stage, I don't want to complicate it with that. Just the magnitude of that current and voltage. Okay? A lot of the time, all you want to know is how many amps are flowing or going to flow, so I can put the right circuit breaker, the right cable in. The phase relationships aren't of interest, then in other times they are of interest. All right? So last one before I give you the tutorial questions to start working on this week. We got three-phase 60 Hertz line connected to 3 identical capacitors. They're in delta. So that's a strange, funny way, but easier way in some ways to connect, show a system connected in delta. Yeah. So if the line current is 22 amps, calculate the capacitance of each capacitor. (22 amps, 550 volts). So we can deal with one. We only need to calculate for one. Yeah. What can we do? We've got no resistance in it at all. What can we calculate? We know IL, 22 amps, and we know EL is equal to 550. What you need to be careful of is this 22 amps. Some of it is going to this capacitor, and some's going that way. So do we not want, if we're going to calculate XC for one capacitor, we need IP, which is 22/√3, and whatever that is. All right. I mean, rather than calculate that there, what you're saying is XC is equal to EL over IL/√3. Okay. And if you do it all in one go, you're not rounding twice. So that's 550 volts divided by 22/√3. Which is 1/2 pi times 2 pi FXC, yes. You're good at spotting my deliberate mistakes, Robbie, aren't you? 2 times 60, I think it is, isn't it? The question, times 43.3 equals 61.3 microfarads. Yeah. So these problems are no different to any other problem you've ever come across. You've got to look at what you've been given and how I can find something else that'll help me find something else that'll help me find the answer we're looking for. All right?